Administratively, as I wrote to you in the email and lost a few students as a consequence, we're going to have an exam. I just thought this is the most fair event to everyone. You will learn the best. Too bad I'm recording, but I'll still say it. So grades are going to be fine, average for the university. You're not going to be any lower compared to other courses. Okay, I don't expect any issues. The student here next to Wahit, I forget your name. Wahit and friend. Your name again? Jeff. Any questions? You're helping him with the homework? No, just okay. No, it's disrupting me if I hear talking. But if you guys have any questions, please ask. So, yeah, as I said, exam on the 8th, I believe, and week after. Oh, you also have the NURIPS? Yeah, so those of you who have NURIPS deadlines, I think we'll just have another date. It's probably not, it's probably a handful of people or something, so we'll just have another exam time, and it doesn't even have to be coordinated with the registrar, or just do it in class or something and find a place and do it in just a couple of hours. Yeah? Any questions? Yeah?
Can we also have the option to take the exam on a later date or not?
If you have a very, very special circumstance, I will allow it. Then just tell me exactly why. You know, you sign the honor code, you have 2 hours, you return, or whatever, 3 hours, how much time, and then, yeah, we'll be able to make it work. But I don't plan to do it. This will be the exception. If you ever, you said you were leaving and never coming back or something like that. Yeah. Okay. Okay. Any other comments or questions or anything? These kids, they wake up at 11 a.m. or something, so yeah, not too early. When?
We have the room for 12 to 5.
12 is good. Or maybe you want to eat lunch before. Yeah, 1 is good. Okay. Yeah? Any other? Okay, so 1 p.m. on the 8th. Yeah. Open. You prefer open? I guess so, right? I mean, yeah, open is fine. But no, let's do it with no electronics. Okay, no phones or nothing allowed into the exam.
Can we have the text? Or should we
Putting me in a conflict of interest here. Actually, I don't get, as you know, I put all my books open source, they're all available. If you prefer it to be on a device, that's fine with me. But the only thing is, yeah, I guess so. But just then don't connect to the internet. How about that? Download it, or, you know, just don't. The temptation to use the AI is very strong. That's what I'm told. That's what I don't want to happen. Yeah?
Your recommendation, what type of content versus just
Entire course. How about that? I mean, there is book 1 and there is book 2. So both of them are going to be covered, which is kind of unusual. In previous courses, I taught only 1 book, and I don't think I did too much more, honestly. I don't know how this class is going pretty quickly, which is very nice. I'm happy about that. Yeah. It's not going to be, the purpose is to just see the beauty of the material. That's really my purpose, so that you will be able to see what wonderful questions we can invent and try to solve them and do your best and express your knowledge. It's not going to be designed to trick you or to be mean in any way. So purely to express our joint love for the mathematics that we're teaching here. That's the point of the exam. And of course, to give you a grade. Yeah, Jerry? I didn't write it, so it's hard for me to say. I think I would be able to because I just know the material, you know, I've been teaching it a long time. But then I'm trying to think of myself as a student. Probably. I mean, I will be able to, once we write the questions, I will be able to tell you maybe to, I prefer there is no electronics at all. So then I'll be able to just tell you, why don't you print out chapters 4, 5, 6 from the textbook, then you don't need an electronic device. That would be easier, right? Yakia?
I mean, I guess
That's right. That's right. That's right. So probably it is a good idea to have some version of the book or lecture notes or something of the forum, and maybe even both books. But I'll just tell you, I mean, I think I'll just tell you in advance maybe. These are the relevant, or maybe print out some relevant material for you. That will be even easier. So I prefer that there is no electronics, just easier in terms of, because that's the whole point of doing it in class, right? You don't have the computer and the AI. So that's what I prefer. We'll figure out something. Wait, I don't know what we'll do. We'll figure out something that like have these printouts or these.
I mean, what we could do is also we could just set of your own that might be,
Mhm.
and that way it's like self.
Yeah, that's a good idea. Maybe we'll do that. Yeah. More questions? Yeah? Sorry? The exam itself? Oh, I think it's handwritten. I mean, how would you, that's, yeah, handwritten, so no computer. You just write down on handwritten, and this, which means the solutions are going to be short in terms of text. You're not going to write a book, so you're going to short proofs. Yeah, more questions? Very good. So today I'm going to talk about linear dynamical systems. And the way we approached it, if you recall, starting from the early days of the course, we talked about decision making and learning in a very general setting and without any generative assumptions on the data. We talked about experts, we talked about decision making, prediction from expert advice, then learning more complicated structure sets such as passes in a graph. And then at some point, we reached a more complex decision-making scenario or learning scenario of LLMs and physical devices and so on. We talked about dynamical systems. So once we started talking about dynamical systems, that was sort of the second phase of the course after the break. We saw that even answering simple questions about dynamical systems are hard. More specifically, even deciding stabilizability or stability of a dynamical system, which is a polynomial, low-degree polynomial, is NP-hard. So that motivated us to look at a more discretized or less efficient formulation of the problem, which we called reinforcement learning or learning in Markov decision processes. And then we gave pretty much a complete solution in the form of the value iteration algorithm that finds an optimal policy. That was, I believe, Thursday. Thursday we did that. Tuesday, sorry. Thursday I was not here. So Tuesday we did value iteration. And if you care about an additional algorithm, we also showed how to formulate the problem as linear programming, and that immediately gives you another way of solving Markov decision processes or reinforcement learning. We ended up with a caveat. So reinforcement learning is not an efficient representation of the problem. In what way? We basically, the methods that we came up with, both linear programming and value iteration, they depend on the number of states. The number of states can be huge. So in any setting that you can think of, pretty much, the number of states is going to be extremely large. If we have a physical dynamical system, all possible states, there are a continuum of states. If you discretize it, it's going to be exponential in the dimension. If we're talking about learning in a language model, again, number of states is going to be extremely large and captures all possible states of the LLM or the network or the brain that generates the sequence. So again, very, very large. So now I'm searching to something which is more efficient. And we have on one hand dynamical systems that are NP-hard computationally to determine simple properties of them. And on the other hand, we have a less efficient representation that allows to solve everything, but in an inefficient representation. So what I want to do now is go back to dynamical system and think of a simpler model or a special class of them and try to derive efficient algorithm for that special class. Make sense where we are? Yeah? That simple class will turn out to be extremely useful for even for nonlinear dynamical systems. So there is a way to extend the linear world into more and more complex settings, and you can think of it maybe just kind of to draw a schematic. If we have RL on one hand and dynamical systems slash control on the other, so these have an efficient representation and these don't. And here we have efficient algorithms and here we don't. That's kind of what we saw. So one way to approach the problem is try to go from RL and try to remove generality and impose more structure. For example, linear Markov decision processes or function approximation and buzzwords which you might have heard about. And the other is starting from here, taking the linear world and try to extend it and make it more and more expressive and more encompassing and try to derive efficient algorithms. Here we already have efficient algorithms, so try to generalize them. And the other is a place where we don't have efficient algorithms and try to restrict the model and come up with efficient algorithms. And that's pretty much the state of the world right now. I cannot tell you that we have a complete answer to this problem, but that's where researchers are on one of these two axes. Does it make sense? So let me talk about linear dynamical systems. I'm starting from the most basic model for dynamical systems and try to derive efficient algorithm for it, and then we'll try to generalize these more and more. What is a linear dynamical system? It is a mathematical model of the following form. So this is the governing equation of linear dynamical systems. X is the state. U is so this is the state. This is the input or control. And this is noise. Then we have A and B. These are called together the system. And they control the entire dynamics. And x0 usually we denote as the initial state. You may notice that this is very similar to a Markov decision process. Very, very similar. What's the difference between this and a Markov decision process? Yeah? Noise is one thing, yes, and that's right. I mean, I have here the noise coming in additively to the process, right? So it looks kind of more general. That's right. Yeah, Ben? Right. So there's a very precise way in which the controller, the input, affects the next state. It comes in linearly. In a Markov decision process, if you remember, I have a policy. The policy allows me to take an action. And then how that action affects the future transition, it's not it is linear, but in a kind of much more verbose way. So it doesn't have to come in linearly like this into the state, right? However, if there is no control, this can be a Markov chain. Okay, so if I think of X as a distribution over states and A is a stochastic matrix, this does look like a Markov chain. So, okay, so no control, it is a Markov chain, or it's even more general than a Markov chain. Could I take this formulation and convert it into a Markov decision process? Yeah, Bogdan. Yeah, yeah, I could. Yeah? Arnav? Well, My question was, given A and B, can I take this and create an MDP, which is usually we denoted by, we had the states, V, we have a transition, T, we have a discount fact, whatever, gamma, maybe starting state, right? S0, forget if we had anything, action set, right? Can I do that? That was my question. And that's actually a good homework exercise to think about, and the answer is, as Bogdan said, yes, I could do it. Maybe my set of states, or usually denoted by S, right? So state of states would be infinite in this case. So all possible vectors in R to the input state, maybe. Actions, again, all possible vectors U. And transitions are defined by this equation here. Okay? So I could do that. It would be incredibly inefficient. I would have infinite many states, infinite many actions, and so on. I could do that. So this is a less general problem. So in one hand, it looks more general, but actually it's less general than Markov decision process. And we have seen examples, for example, the double integrator, your book contains more, that show how to model various physical systems as linear dynamical systems. Linear time invariant or sometimes time varying dynamical systems. We talked about the double integrator in particular, if you remember. The car with the 2x2 matrix, so it's a very simple kind of dynamical system. Okay. So I could create a Markov decision process and kind of solve everything there is to solve over this dynamical system. Nevertheless, it's an overkill. So I hope it's clear that it's an overkill. I would like to kind of answer and ask the basic questions of stability, controllability, without going to the MDP world and discretizing to very fine precision and having exponentially many states and actions. So that's what I would prefer to do. So let's ask all these questions that we asked in the lecture 2-3 lectures ago, I forget when we just started talking about dynamics, and analyze these particular simple forms of dynamics. So question 1, is AB stable? So stable, when we talk about stability of a system, we usually talk about without input. We usually have a closed. When we have an input, we usually call it stabilizable, stabilizable. But even simpler is A stable. So if you remember, we defined what a stable dynamics means. It means that when we have xt plus 1 is f of xt, we ask whether for every x0, does xt go to 0? Is there a policy that makes this kind of closed loop dynamics go to 0 as t goes to infinity or not? Okay, so this is without a policy. If we have a policy, stabilizable means what? Stabilizable means, does there exist a policy? Policy means pi of x equals u. So there is pi of xt equals ut. So there is a ut I can keep on adding to the system in such a way xt goes to 0 as t goes to infinity. Yeah?
You have to say something about the reduce time to explode and
Yeah.
you have to say something about that.
Right. We called it, I think, bounded input, bounded output. This was 3-4 lectures ago. You can have quantitative definitions, meaning, okay, what if I don't allow u bigger than 1, or some kind of arbitrary number, and so forth. So even this is kind of this is an asymptotic notion. You can make it finite. So for every epsilon, there is a t such that xt is bounded by some epsilon. For this point in time, I'm going to make do with these asymptotic notions, because the extension to quantitative definitions is very straightforward, okay, which we can discuss. But let's start with stability and stabilizability. Is this, so in general, if you remember, we couldn't even ask this, and we couldn't even answer this very simple question for a nonlinear dynamical system. And now if I ask it for linear, now I restrict myself to a linear dynamical system. What is the answer for stability, if a given dynamical system is stable or not? Arnav? Okay, so Arnav's answer is yes. We can determine if A is stable. And I think you're saying that's if and only if for all eigenvalues of A are less than 1. I believe that's what you're saying, right? Yeah, less than 1. Okay. I mean, there could be 10 of them that are half. That's fine, right? So, yeah, that is a correct characterization. So we have a definition for that, which is called the spectral radius, rho of A. This is the spectral radius. Of A. Let me define it. Precisely. And it is given by the following. So, or I should say there is a fact. So rho of A is less than 1 if and only if the limit t goes to infinity a to the t. Here I take the spectral norm of A is 0. So you might all be used to symmetric matrices. In symmetric matrices, all symmetric matrices are orthogonalizable above the real numbers, and it's kind of easy to argue about. It's easier to argue about diagonalizable, so I can talk about the diagonal, and it's easier to talk about them. This asymmetric matrices are a bit more tricky. They require a bit more machinery. Spectral norm. So spectral norm is defined to be just the largest, so A2, this is equal to the max x ax divided by x. Euclidean, this is Euclidean norm. Okay. Yeah.
How is the spectral radius?
It's hard to define it. So, but you can think of it as the largest. So let me define it for diagonalizable matrices. So if A is diagonalizable, then rho of A is equal to the following. So I take A u d u inverse. This is diagonalization of A. And then I take rho of A to be the max I dii. I define it to be this. So it can be a complex, so asymmetric matrices are diagonalizable over the complex numbers, or not all of them, but it's a dense set. I'm doing a bit of linear algebra here, okay? So it becomes more complicated for asymmetric matrices. U doesn't have to be have to be orthogonal. It doesn't have to be orthogonal. But nevertheless, if you take any matrix A and you perturb it a bit, then it does admit a diagonalization over the complex numbers. I can write it like this. So D is diagonal. And then I define it to be the magnitude of the largest eigenvalue. And now what I wrote here, the fact, so it's less than 1 if and only if the limit goes to 0. Okay, otherwise, it doesn't have to go to 0. It can cycle, it can explode if it's bigger than 1. More generally, so any A, it can be written in this way, but it can have a Jordan form. So it might be the case that D is not diagonal, it's a Jordan matrix, if it has a multitude of eigenvalues. That's why I'm being a bit careful here. Nevertheless, I'm assuming that, so this, the set of diagonalizable matrices over the complex numbers is dense, which means if I take a very small perturbation of any matrix, for any purposes, all the matrices are diagonalizable over the complex numbers, okay? For our purposes in this course. You take a small perturbation, it's diagonalizable. So there's no Jordan form. I can write it like this. U can be very big. It doesn't have to be orthogonal, but I can always write it like this with a diagonal D. Do you remember this from linear algebra? Yeah? Math students? Yeah? Okay? Where's Ellie? Yeah? Okay what I'm saying? Okay. Yeah. Any questions? Yeah? Yes. It's not. Operator norm is what I wrote here. So it's this ratio between Euclidean norm of AX divided by X. So what happens is you could have, so here is what can happen. What happens when I take, it's not the operator, oh, I should say. Okay, let me, I have a, so this needs to be multiplied by, so U inverse, if I really want to be something like that. So the row of A is multiplied by the maximum eigenvalue multiplied by the orthogonalization matrices. So what happens is you could have a maximum eigenvalue that's smaller than 1, but U is very big. So in one step, you're going to have a larger number. So even though the eigenvalue is smaller than 1, this is going to be smaller than 1, you blow up. So in the short term, you can blow up and then go to 0. This doesn't have to be monotone. This series here, it's not a monotone convergence. That's what makes it kind of tricky. It's a very interesting phenomenon that happens here. Let's write it down and see why I'm saying. Let me prove this fact, okay? I want to prove this fact. I want to prove it. So let me proof. Okay. So if for every x0 we have that xt goes to 0, xt goes to infinity, then what is xt? Xt equals a to the t x0, right? So this means that for every x0, a to the t x0 goes to 0. And this means that the limit, as t goes to infinity, a to the t is 0. Because for every starting vector, I have this kind of thing. This value goes to 0. On the other hand, other direction, if row of A is less than 1, then A can be written as U d U inverse, with d less than 1, dii less than 1 for all I. Okay. Now, look that xt is equal to a to the t x0, which is u d u to inverse to the t x0, which is equal to u d to the t u x0. So far? And this is bounded by max I dii to the t times d times x0. And this goes to 0. As t goes to infinity, because dii is less than 1. Yeah? Correct, correct. So there is a lot of subtlety here, but it's actually an important subtlety. So operator norm means I have, in every single step, the magnitude of my state decreases. This is an interesting condition, but it doesn't capture the full interesting thing that happens with linear dynamical systems. They could blow up and then go down, okay? That's a much more interesting situation. In fact, that captures the full power of linear dynamics. And it's very important when we'll talk about nonlinear dynamical systems, because you rarely expect that there is a monotone convergence. Many times it kind of looks diverging and then starts converging. So this is the phenomena that happens here. It happens exactly because of this diagonalization here that is not necessarily orthogonal. Questions? Yeah? Little d, oh, you know, that's like the dimension, so dimension of x0. Because I'm replacing it by only one coordinate. I guess I didn't. I could have done it by, if you want, I can just do this. So x0. That's also fine. Yeah. Because it's bounded by, right? So this is bounded by identity times what I wrote here. Times, I guess, the, oh, u inverse. Yeah. Right. So I'm bounding this by the largest eigenvalue of d times the magnitude of u times the magnitude of u inverse. Okay. No, you cannot. It doesn't commute. Yeah, it doesn't commute. Even diagonal matrices don't commute. If it's diagonal and something else, it doesn't commute.
But u is
U is square, yeah. But even with a square matrix, you multiply it by a diagonal from the one side, it's not the same as if you multiply it by a diagonal from the other side, right? One multiplies the rows and one multiplies the columns. Any questions? Are we okay? I feel it goes into the details of linear algebra here, and it seems, why am I diving into the orthogonalization of complex matrices? But actually it's inherent. It's inherent in linear dynamics. Many interesting dynamical systems are non-symmetric. For example, the double integrator we talked about, there are many other examples. They're not symmetric. Actually, double integrator is symmetric, but there could be others that are non-symmetric. They're very interesting. More questions? Well, that's good news, okay? I can talk about, I guess partially good. I can at least characterize when a linear dynamical system is stable, which is good. I couldn't do it for nonlinear system. Is there an efficient algorithm for that? I have a nice linear algebraic condition here. Is this efficient to verify? Any comments? Yeah? Yeah, you can do Gaussian elimination. I guess it doesn't immediately apply to any matrix because you might have Jordan form, right? But perturb it. Let's say perturb it a little bit, then it's diagonalizable. Then you can do the diagonalization over the complex domain by, I guess, Gauss. What's the name of that? I forget the name of the algorithm. But Gaussian elimination, right? So Gaussian elimination will give it to you. Yeah?
Is finding the right perturbation calculus?
Oh, I'm saying for any perturbation. There's probability 1. So when you have a matrix which is complex, any perturbation you apply to it, you will get which is, let's say, Gaussian. Doesn't matter how small or large. With probability 1, it becomes diagonalizable. All you need is that all the eigenvalues are distinct. Okay. Other questions? Well, okay. Stability is fine. Great. What about stabilizability? So this means I'm getting A and B. I now have two inputs, and I want to know if there is a sequence of controls that will make it go to 0. That's my question. Is this characterizable for a linear dynamical system? Remember, this was a problem for nonlinear, right? Any ideas? Yep.
I mean, I want to say yes, that it'll be something along the form of like if the spectral radius of P is greater than the spectral radius of A.
Hmm.
Something similar.
Okay, but give me something a bit more precise. I mean, the A and the B, so you could have or I would say many interesting cases are when B has a different dimensionality than A. So the state could be huge, but your control over it is not full rank. It's not immediate. So if they're the same dimension, these are both square matrices, it's kind of an easier situation, and I think what you're saying will work. But many times you can have like a state that's in high dimension, so this equals this times that, plus this times a number, okay? So the way that the control comes in is via, or this times a number, is via a scalar. You can only control, you have some kind of power or force that you can apply. It's going to affect via some vector the state. But you can't affect the entire state. You can only affect a certain direction. Is the physical intuition clear of what I'm saying? That's kind of an interesting, this is the interesting case usually. And then here, it's not immediately clear what does stabilizable mean, I guess. Right? We know what it means in generality. There is a sequence of controls that will make it go to 0. How can I determine it? What do you think? Any ideas? Yeah, yeah, Alex? Uh-huh. Excellent. Okay. Let me go over Alex's suggestion, which is very good. So let's restrict ourselves to very special kind of policies, those that are linear. That's what Alex is saying. Why will we do that? I don't know. Let's start somewhere. So let's consider policies that are linear policies. So this means that ut is going to be equal to k times xt. So it's a linear function of the state. Now can we ask, is there a linear, what is stabilizability for linear policies? stabilizability now becomes the following question. Does there exist a K such that A plus BK is stable? You agree? Now, if A plus BK is stable, we know how to answer that, right? That we already know. So this means, is there a K such that A plus BK, rho of this thing, is less than 1? Okay? And it turns out, so theorem, AB is stabilizable if and only if there exists a K such that rho of A plus BK is less than 1, and this can be found efficiently. Okay. So let's do direction 1. Suppose there is a K that makes it stable. Why is the system stabilizable? Yeah, Arnav? Right. So yeah, I mean this direction, let's take K. Now what is xt? Xt is equal to A xt minus 1 plus B ut minus 1 plus noise, but in our kind of simplified notion of stability and stabilizability, we're noise free, right? I mean, we can add noise, this will be bounded input, bounded output. I'm removing that. This is equal to what? It's equal to A plus BK xt minus 1, right? And this equals ta 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 A plus BK to the T x0. And this goes to 0 as T goes to infinity for every x0 by the definition of spectral radius. So that's this direction here. It turns out that the other direction is also true. So if the system is stabilizable, it must be stabilizable by a linear policy. That I will only prove to you Thursday. Okay, I'm not going to prove it to you today because somehow it's nicer to do it this way. So I'm going to show you something a bit stronger Thursday that proves the other direction. That's less obvious, I would say. So other direction on Thursday. But it is a very beautiful direction. Yeah, Connor? Correct. Yeah, so for the notion of stability, stabilizability and stability I talked about a couple of weeks ago, it was noise-free. I also gave you a bounded input, bounded output notion. Now, I claim that what I showed you is basically bounded input, bounded output. Can someone see why? Maybe it's not trivial to see, but suppose I have, no, not you, Rohit, I know you know it, but someone else. Anyone can see why? I guess it's non-trivial, but let me show you the calculation. So So BIBO, bounded input stability, or stabilizability. So suppose WT is less than 1 for all t. So I have a bounded input, okay? Now, xt is what? Let's look at the norm of xt. This is equal to, by this equation here, I have the norm of axt minus 1 plus bk xt minus 1 plus wt minus 1. Okay? So this is less than, I have here a plus bk xt minus 1 plus wt minus 1. And this is less than, ta-da-da-da-da, I have here summation over I from 1 to t, a plus bk to the I, wt minus I. Right? So I from 0. Okay? So this is going to be bounded by Cauchy-Schwarz 1, the norm of these w's. Okay? And then I have basically summation I from 0 to t, norm of a plus bk to the I. Okay? Now, suppose the largest eigenvalue here is some gamma, which is less than 1. Then this is bounded by what? Not gamma, but 1 over 1 minus gamma, right? So this is less than summation I from 0 to infinity of gamma to the I, which is less than 1 over 1 minus gamma, where gamma is the largest eigenvalue. So it's kind of a sketch I'm doing here. But it implies, you see that the bounded input, I get bounded output if I know that this spectral radius here is strictly less than 1, that I get that. Okay? So I kind of prefer to go lecture today without noise, but you can make it into a noise case. It's going to be always bounded. That's kind of what we care about. System is going to remain bounded even if I give it noise. And otherwise, it's not going to be bounded at all. Or if it's an unstable system, it's going to go haywire. Yeah? Questions? Yeah?
That first has to be equal to this.
Over here?
Yeah.
It's equal, yeah. But it's also correct.
Yeah.
Yeah.
I just want to make sure I
Yeah.
understand this.
Yeah, yeah. More questions? Okay. So the question of efficient algorithm for this problem, I'm going to give you on Thursday, and that will also complete the second part of the theorem. I now want to look at a stronger property of controllability. And that has the advantage, it's also kind of easier to analyze. So controllability of linear dynamical systems. So this is a stronger property than stabilizability. I don't want to just drive it to 0. I want to drive my system to any final state. For example, in the double integrator, I had a target state, and I wanted to apply force in such a way to drive it to the desired state with minimum power or with whatever constraints. So remember, I'm going to again talk about noise-free, but actually noise-full or bounded control, all these things apply also to noise. So I want from any x0, I want to get to x star by sequence x1 up to xt. This is what controllability means. There is a t, there is a sequence of inputs, so u1 up to ut. So I'm going to give it a sequence of u1 up to ut, and what I want to happen is I want my system to go to the state that I desire. Yeah, question?
So
Exactly. Exactly. So, yeah. So noise free. Noise free, I want to reach exactly this final state. Yeah. Well, let's say B is identity. Okay. Is the system controllable for B equal identity? Let's kind of get some intuition. So question, kind of bonus question, if you will. So B is identity. I get A. Is it controllable? How do I know? Yep. Sure, there is no B. So there's only, yeah, B is identity. Yeah. How do I know? Yeah, Connor?
Well, I guess it depends.
It has to depend on A. Because what if A is 0? It's not controllable. It cannot do nothing. It will never get to anything besides the initial state, right? So, David? Okay, but has to go for every, you're right. I wanted to apply to every X star. You're right. So what does it mean? Yeah, controllability means for every X0, I want to get to every X star. And from any to any. Aha, very good. Okay? Very good answer. So the answer is, if and only if A is full rank. By what David said. Okay, I want to get from every X0 to X star, from every X0 to X star. And I can do that only if A is full rank. Otherwise, I cannot do that. Yeah, Arnav? Yeah, you can do that. Let me see. So is it? You're right. Sorry, you're right. That is true. So I take it back. So, actually, the answer is if and only if. I will show you in a minute. I'm writing something trivial, but you will see how I generalize. So if identity is full rank, which it is. So basically, the answer is yes. So yes. No, but actually, the discussion here was good. I mean, I now want to move to the case that B is non-identity. Okay. So, but thank you. This is a correction. It looks like I said something trivial. It's not trivial, and also David didn't say something trivial. So now let's go to the general B. Now how do I know if I can move from any vector to any other vector? And you can see that you can't just say what Arnav said, oh, just take xt minus x0 and put that in. It's not going to work. It's going to be multiplied by a b, right? So now what can we say? Any ideas? Yeah. Very good. Okay, very good. Slightly more refined than that, but that's kind of the idea. Check and see what? Okay. Yeah, that is correct. That is correct. So what I want to happen is I want to give the u. There is a transfer function from u's to the x. Okay? There is a transfer function. Let me derive that. So what is xt equal to? It's equal to a xt minus 1 plus b ut minus 1. And that's equal to a xt minus 2 plus ab ut minus 2 plus ut minus 1. And that's equal to ta 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 ta. So what do I get? In the end, I get something like ax0 plus, sorry, a to the t x0. Then I have at minus 1 b ut minus u1 plus ta 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 up to ut minus 1. That's what I get when I open the whole thing, right? But minus 1. So therefore, I can rewrite it as the following. So xt minus a to the t x0 is equal to this matrix, which is a to the power t minus 1b, a to the t minus 2b, ta 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 ta, b, times the concatenation of all these vectors. So I have here u1, u2, ut minus 1. Now, what I want to happen is, I want this to be equal to any vector in the world that I might want to create, right? So I'm asking, can I create any vector in the world by a product of these things times some input? What happens when B is identity? Well, like David and Arnav said, okay, B is identity, I don't need all this stuff. B is identity. I can put here U, whatever U I need to make it equal to what I want to happen, right? But if U is not identity, if B is not identity, then I have some system of equations here. So let's call this matrix here, this is called the Kalman matrix of order T as a function of B, A and B. Kalman AB. And the theorem says that AB is controllable if and only if the rank of Kalman dx AB is dx. So it's full rank. Full row rank. It's D by something, by du times T or whatever. T is dx, then it's theta. It's basically du times dx. And I claim that the system is controllable if and only if it's full rank after I do d iterations of these powers, d powers in the worst case, maybe less. Jeff, you have a question. What's the question? Oh, let's look. What is the size of this? Is a rectangular matrix, okay? So the row space, this space here, so Kalman of AB is in reals. So it maps to a state. State is dx. That's what it maps to. And what does it take as an input? It takes as an input, we have, depending on the order, so T and H1 is du, dimension of input. So T du. That's the dimensions of this matrix. Yeah, Connor? Rank of the Kalman matrix with dx many powers, is equal to dx. That's the condition. X is the state. So I have this matrix which I define to be all the powers up to t, take t to be dx, the output. It has to be at least dx, because in the worst case, maybe du is 1. You have 1 input. And then the output is million. You need at least 1 million of these things to kind of to be able to reach every possible component. The rank is not going to be full after less than 1 million powers, right? So it's just going to be like a narrow, too narrow of a matrix cannot have full rank. For it to be full rank, you need to fill it up. And I claim you never need to fill it up by more than dx. At that point, you have enough to get full rank. If you reach to full rank, you're controllable. Otherwise, you'll never, ever be controllable. That's the claim. before I prove it, any questions? Yeah? At most, at most, yeah, at most. So that's a good remark here. That's a very good remark. So the conclusion from this condition is, I might have to apply dx many iterations before I can control the system. Remember that my first question, identity, I don't need one iteration. I don't need to do any iterations, 0 iterations, right? Immediately I put in where I want to reach, it reaches it. Et voila. But if B is a small, I have a mismatch between, that's kind of the more common situation. You cannot control the entire state of the airplane by the engine. You can control some things. You can the velocity or whatever, but you cannot control the whole thing. You cannot teleport it from one point to another. Okay, so that's kind of the more common situation. In the more common situation that your control input is lower dimensional compared to the state of the system, you might need a lot of iterations. And how many iterations do you need? It's at most the dimension, never more than that. Could be fewer. So fewer, it could be fewer, but not fewer than, who can give me a lower bound? It's at least dx by du, the ratio of these things, right? I mean, you cannot, the rank can grow by something every power that I add, but it cannot grow by more than the number of columns that I add. That's maximum it can grow by. This is a linear algebraic kind of class we're doing here today. I hope you like linear algebra. I think it's an interesting application. So it's a very linear algebraic characterization of what goes on here. We will see that actually linear algebra is crucial for understanding even nonlinear dynamical systems, and to that extent, even LLMs and sequence predictors. So it's very, very important. Questions? No questions? Let's prove. Okay, proof. Suppose K T of AB has rank dx. Dx means the dimension of x, state dimension. So who can tell me why it's controllable? Why the system is controllable? Let's say it has full rank. Yeah. Yeah, I don't even think it doesn't have to be invertible in that sense. I mean, you're right. You can take, I mean, inverse is, it could have dimension which is bigger than, it's a rectangular matrix in generality, right? It could be dx by more than dx. So, but it's true what you're saying. There is some pseudo-inverse notion that you can take, or can solve a system of linear equations, right? So, actually, this is kind of both directions, what I'm going to say now. So, we have xt minus a to the tx0, this vector. So let's call it v. V equals Kalman of AB times u1 up to ut. This is the system of equations that we arrived to. Now, suppose that the Kalman has full rank. What does it mean in terms of my ability to generate any output? So, fundamental theorem of linear algebra, right? That's what fundamental theorem of linear algebra says that this system of equations has a solution for every input and for every output if and only if this matrix is full rank. That's exactly what it says. Okay? Yeah? I think that's it. Everyone with me? That's what this theorem says. So this is by fundamental theorem of linear algebra. Eli, correct me if I'm wrong. Yeah, this is the fundamental theorem of linear algebra, right? Full rank? Yeah. Okay. Says that K has full rank if and only if for every V there exists a U1 to UT such that V equals to K U1 up to UT. So this system of equation has a solution if and only if the matrix has full rank. That's by definition. So the dimension of the null space is 0 and so forth. Okay. There's no null space. There's no null space here. You can reach any vector at all. Now, so du could be 1, which means that t is at least dx. Otherwise, there can be no full rank. You cannot have a matrix that's dx by something smaller than dx and has full rank. On the other hand, I claim that t is less than equal to dx. I never ever need more than tx iterations to reach full rank. So this is, I think, what you're saying. In d iterations, you can reach any vector. You don't need more than d iterations. Why is that? Yeah, Alex? That is correct. Yes, that is exactly right. So you were going to say, Arnav?
Oh, I actually.
There might not be, but it doesn't necessarily imply that you don't need more than d, you see? I agree they're not, but why does it imply that you don't need more than them? There is a bit of a kind of, there is something to prove here. So let me prove that. So this is kind of a nice proof. So I claim that, let's look at t equals 1, 2, up to dx. And I claim that the rank of kt, if the rank of kt equals rank of kt minus 1, if this happens, if I increase the t and the rank didn't increase, then it will never increase again. It will never increase. So this means that I only need to take dx if I want to see if I reach the maximal rank. It can only increase by, it increases by at least 1 every iteration. Can be no more than d, because at d, we have, that's how many rows we have, cannot be bigger than d. And if we increase by 1, it can happen at most d times, and after that, if it's equal, didn't increase the rank anymore. Okay, so I never have to do it again. Make sense? So t is at most dx. Now let's prove this thing. I want to prove that if the rank stays the same, it will never increase. So if RT equals RT plus 1, where RT is the rank of KT AB. So RT is the rank of the Kalman matrix of order T. Suppose RT equals RT plus 1. Then span of, I have here B, AB, ta 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 ta, AB to the T, A to the TB, equals to the span of B, AB, ta 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 ta, AT minus 1B. Because it didn't increase, so the span didn't increase. Now, the span is contained under linear transformation. I can multiply this whole thing by A, okay? So this means multiplying by A doesn't increase span if I multiply by A on both sides. So span of AB, ta 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 ta, A to the T plus 1 B is contained in span, well, it's equal to, so in particular contained in AB up to A to the T B. Okay. And if I add B to both matrices, it also doesn't change the containment. Containment remains if I add the same thing to both. Okay? So adding B, I get span of B, AB, ta 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 ta, A to the T plus 1B is contained in span, if it's also equal to, okay? So I could have replaced by equal to. B, A to the TB. And this means that RT plus 2 equals RT plus 1. So it never ever changes. Once I kind of reached steady state, I'm not changing the rank anymore. It remains the same. Okay? And by induction, for all T up to infinity. So what I proved to you by this operation of adding another A to the power times B, I can increase the rank, but if I don't increase it, it remains the same forever and ever. Now, since rank Kalman T for any T is bounded by dx, rank can increase at most dx times, so T less than equal to dx. So that's it. So I spent most of the time kind of proving to you the expressivity of this Kalman matrix. So it can grow, grow, grow. At some point it doesn't grow anymore, at which case it becomes stale. And the rank of it is what determines the expressivity of the whole system, if it's controllable or not. If it's full rank, it's controllable. If it's not, you get stuck at some point. Doesn't matter how many more iterations you take, you were never ever going to reach some places in space that you didn't reach before. Questions? So, to summarize, what we talked about today are properties of linear dynamical systems. They're a special case of dynamical systems, very special case. But in contrast to what we saw for polynomial systems, they are much better behaved. We can determine if they're stable, if they're stabilizable, if they're controllable. Of course, this is polynomial time, right? Determining the rank of a matrix is efficient. You can do it in polynomial time. You can see what the null space is. So it's much better behaved. That's the point I wanted to deliver. And on Thursday, we're going to see it's better behaved in a much stronger way even. Not only can I determine stabilizability and controllability, I can actually optimally control these systems very efficiently. So we're going to see, this is kind of the hallmark of, I would say, all of optimal control theory. It's called LQR, and we're going to study it on Thursday. And after that, we're going to move on to really new stuff, which is nonlinear dynamical systems, spectral filtering, and sequence prediction, and so on. So Thursday, I'm going to wrap up classical control. Okay? See you Thursday.